You've probably heard about large language models, or LLMs, doing some, well, truly incredible things, writing intricate code, tackling complex math problems, even, crafting compelling stories. They seem to be constantly expanding their
Oh,
capabilities.
absolutely.
But here's a persistent puzzle, isn't it? How do these models, which are often trained on very specific data sets for specific tasks, suddenly get good at completely different, seemingly unrelated areas?
Yeah, that's the thing. It's a phenomenon that's intrigued researchers for quite a while now.
Huh.
Imagine training a master chess player, right?
Yeah.
And then one day they just spontaneously become this brilliant, accomplished painter.
Right. It feels like that sometimes.
It does. And for a long time, the underlying how behind this kind of cross-domain generalization in AI,
Hmm.
well, it's remained a pretty significant mystery.
Indeed. And today we're going to really dig into a really interesting new paper that offers a compelling idea about that puzzle. It's titled Proto-Reasoning: Prototypes as the Foundation for Generalizable Reasoning in LLMs, and it's coming to us from ByteDance Seed and Shanghai Jiao Tong University.
Right.
So our mission today is to unpack their bold hypothesis that LLMs achieve this impressive cross-domain generalization because they recognize and apply what the authors call reasoning prototypes.
Yeah, think of these prototypes as like fundamental thinking patterns, the underlying abstract structures that you find in seemingly diverse problems.
Okay.
So we'll explore the proto-reasoning framework they build, try to understand how it helps LLMs grasp these core patterns, and why it seems to be showing such remarkable results in boosting reasoning capabilities kind of across the board.
Okay, so let's start maybe by looking at this mystery of generalization in a bit more detail. We've observed large reasoning models, or LRMs, particularly those trained with long chain of thought reasoning.
Long OT.
Yeah, that's when a model explicitly shows its step-by-step thinking, right? These models display truly remarkable abilities to generalize.
That's right. I mean, take models like DeepSeek R1. Originally trained heavily on mathematical and coding problems, sure, but then they suddenly demonstrated capabilities in pretty unrelated fields, general STEM questions, even creative writing.
Wow.
And there was another model, Logic RL, which showed it could transfer its skills from solving logical puzzles directly over to mathematical reasoning.
Huh.
It's like these models are extracting something universally applicable from their training data. But the big question has always been, what exactly is that core something?
And this is where the core insight of this paper comes in, right?
Exactly.
The researchers are proposing that this cross-domain generalization isn't, some sort of digital magic. Instead, it stems from shared abstract reasoning prototypes.
Yes, these are fundamental core reasoning patterns, thinking structures that are common across entirely different domains. Their hypothesis is actually quite elegant, really.
Ah.
Well, they suggest that when two problems, even if they look totally different on the surface, share the same underlying reasoning structure in their solution, that's when strong generalization naturally happens.
Right.
The model learns that core structure, kind of internalizes it, and then it can apply it effectively wherever that structure pops up, no matter the specific context of the problem.
Got it. And that brings us to proto-reasoning itself. So it's essentially a blueprint for better thinking, designed specifically to test this hypothesis and leverage these isomorphic processes, meaning structurally similar ones, to significantly enhance LLM capabilities.
And what's particularly innovative about proto-reasoning is that it's built on these powerful prototype systems. These aren't just abstract ideas. They're formal, expressive representations paired with really robust verification systems.
Verification systems. So.
Yeah, and this combination lets them formally capture these intricate reasoning patterns and, crucially, confirm if a solution actually follows that pattern correctly.
So what does this framework actually do then? It sounds like it has some pretty powerful capabilities.
It definitely does. It includes an automated pipeline. This can convert natural language problems directly into these abstract prototype representations.
That sounds like a key step.
Oh, it is. It's not just translation. It's critical.
Yeah.
By standardizing how problems are represented, the models can focus purely on the underlying logic, not get bogged down by all the nuances of human language. This kind of uniform language of logic is key to spotting those abstract prototypes.
And beyond that, you mentioned a verification system. Provides reliable feedback. That must be crucial for training.
Absolutely crucial. And maybe one of the most powerful features is its ability to synthesize, basically generate, an arbitrary number of brand new problems within that prototype space,
Right.
while guaranteeing their correctness. That's a huge step forward for generating high-quality training data at scale.
All these innovative features, they need a solid structure. It
Huh.
sounds like this proto-reasoning framework is built around two core modules that really drive its capabilities.
Precisely. Two main components. First, you've got the prototype constructor. That's the bit responsible for transforming problems into their specific prototype representations.
Okay.
And second, the verification system. This module evaluates whether the model's outputs, once they're in these prototype representations, are actually correct.
Which then raises an important question. If you're building a system based on prototypes, what kind of prototypes did they actually choose, and why those specific ones?
Great question. They picked two very specific, well-established languages, Prolog and PDDO.
Prolog and PDDO. Okay.
And the choice wasn't random. It was based on three key characteristics. First, they are declarative. That means they focus on describing the problem, not the step-by-step solution. This helps preserve the natural reasoning structure.
Interesting.
Second, they're highly expressive. They can capture complex relationships and state transitions really well. And critically, third, they are verifiable.
Ah, verifiable.
Yeah, they have mature automated interpreters that can rigorously check reasoning chains for correctness. And that's essential if you want large-scale automated training.
Okay, let's talk about Prolog first then. Used for logical reasoning. For someone who might not be familiar, what exactly is Prolog?
So Prolog's short for programming and logic. It's essentially a language for defining relationships and rules. Imagine creating a very precise instruction manual for a computer.
Okay.
Where you lay out all the facts, like Socrates is human, and then define rules about how those facts connect. Like all humans are mortal.
Right.
So instead of telling the computer how to solve a problem step by step, like in most programming, you tell it what the problem is and what rules apply, and it figures out the solution based on logic.
And how does that way of thinking line up with how humans actually approach logic problems?
It actually aligns quite naturally with our own, human deductive inference, pattern matching, relational reasoning. For instance, in the paper, they give an example. You can define facts like human Haruki or likes Tuma Haruki. Then you define a rule like friend XY if human Y likes XY and likes YX.
Got it. A logical definition of friend.
Exactly. And once you've set up those facts and rules, Prolog can answer queries like who are Tuma's friends or is Setsuna a human? It directly mimics that logical deduction process we often use.
So how did they build a system robust enough to handle something like logical reasoning in Prolog? Were there specific challenges in creating that construction pipeline?
Well, the brilliance of their approach, I think, lies in this four-stage model-driven construction pipeline. It essentially automates creating perfect training data.
Okay.
It starts by collecting real-world reasoning problems from the web. Then they use LLMs to transform those natural language problems into formal Prolog representations, and importantly, standardize the outputs, often using JSON.
Standardizing, right.
Then stage 3, the system systematically increases the problem complexity. It makes harder and harder problems on demand while keeping that output format consistent.
Clever.
And finally, stage 4, they use a standard Prolog interpreter to automatically generate the ground truth answers. Now, this last step is a real game changer.
Why is that?
Because it completely removes the need for manual, human-labeled question-answer pairs. And it allows for continuous evolution of problem difficulty without accidentally introducing inaccuracies. Huge advantage.
And verifying the model's outputs in this Prolog system, how does that work?
Pretty straightforward, actually. All the correct answers are structured as specific JSON dictionaries. So the training system just tells the LLMs to generate their predictions in that exact same JSON format.
Ah, so it's a direct comparison.
Exactly. Makes it very easy, very rigorous to just compare them and confirm correctness.
Okay, now let's switch gears to PDDL, the Planning Domain Definition Language. They use this for planning tasks. What is PDDL and how does it differ from Prolog?
So PDDL is the standard language for automated planning problems. While Prolog is more about logical deduction, PDDL is focused on modeling state transition systems.
State transitions, meaning?
It defines what constitutes a given state, like the position of tiles on a puzzle board. Then it defines what actions can be taken, like sliding a tile. And crucially, how those actions change the state, moving the tile, changes the board configuration.
Okay.
Think of it like mapping out a world, defining what actions are possible, and then finding the best sequence of those actions to get from a start state to a goal state.
And how does that align with how we humans think about planning?
It mirrors it quite closely, actually. We consider preconditions before we act. Do I have my keys? We predict the consequences of our choices. If I take this route, I'll hit traffic. And we often break down larger goals into smaller, actionable steps.
Makes sense.
Yeah, like the classic N puzzle, that sliding tile puzzle. PCDL can precisely define the grid layout, that's the domain, and the specific scrambled puzzle setup, that's the problem. Then a planner can find the optimal sequence of moves to solve it.
So for PDDL, they used specialized tools to create problems and find the best solutions. And they also came up with 3 distinct types of planning tasks.
Yes, exactly. These tasks were designed to test different facets of planning. First, there's plan generation. Pretty straightforward. The model creates a full action sequence from the start state to the goal state.
Okay.
Second, plan completion. This one's trickier. The model gets a partial plan and has to fill in the missing steps. Requires more sophisticated reasoning about context.
Right, connecting the dots.
Precisely. And third, plan reordering. Here, the model gets a jumbled list of all the necessary actions and has to put them into a valid sequence. Really tests its understanding of dependencies and preconditions.
The verification for PDBL sounds a bit more complex than Prolog's direct match, especially since, as you said, multiple valid plans might exist for a problem.
That's right, it is a bit more nuanced. Unlike Prolog needing that exact JSON match, PDDL tasks can often have multiple correct solutions. So they used a sophisticated PDDL plan validator called VAL, along with custom procedures for each task type.
How did that work?
Well, for plan generation, the output plan has to pass the VAL check, confirming it's valid, and sometimes they might check if it meets optimality criteria, like being the shortest plan.
Okay.
For plan completion, the model's generated plan must not only be valid according to VAL, but it also has to integrate the provided partial plan steps exactly as given in their original positions.
Ah, so it respects the constraints.
Exactly. And for plan reordering, the final validated plan must contain the exact same set of actions as the original unordered list, just put in a correct sequence. This allows for flexibility but still maintains rigorous checking.
This sounds like they needed an absolutely enormous amount of data to train these models effectively. What was their strategy for scaling up the data generation? Did they just manually create thousands of problems?
No, that's the beauty of it. What's truly ingenious about this prototype approach is that because these prototype systems, Prolog and PDDL, have built-in verification, they can automatically generate vast quantities of diverse and, most importantly, correct problems.
Without needing manual human annotation.
Precisely. That provides huge scaling potential. They're not bottlenecked by laborious, expensive human labeling. They can just generate tons of high-quality data automatically.
So how did they actually translate that capability into their training process? The paper mentions a 3-phase supervised fine-tuning, or SFT, process, and they used a powerful LLM, DeepSeek R1, as a teacher model.
Exactly right. So phase 1 was teacher model distillation. They had DeepSeek R1 generate explicit, step-by-step reasoning chains, that long chain of thought we mentioned, for an initial set of problems. This enriched the data with detailed reasoning paths, showing how to get to the answer.
Okay, that makes sense. Teaching by example. And then phase 2 was difficulty stratification. That sounds particularly interesting.
It really is. They evaluated each problem generated in phase 1 multiple times, seeing how often the model got it right. Then they categorized them by this pass rate: challenging, intermediate, or elementary.
And the key part?
The key part is they excluded problems that were either always solved perfectly or never solved at all. They focused the training specifically on the most informative problems, the ones where the model was kind of on the edge, getting some right, some wrong. That's where the best learning happens.
The sweet spot for learning? Makes sense. And finally, a quality filtration phase.
Yes, a final round of really stringent quality control, basically rejection sampling to filter out any lower quality or perhaps slightly incorrect reasoning chains that might have slipped through from the teacher model.
Got it.
This ensured only the most robust and informative examples were used for the final fine-tuning. And the result was thousands of highly refined Prolog and PDDL problems, perfect for training these models effectively.
It sounds like they've engineered a truly sophisticated system here for generating and verifying this unique training data. But of course, the million-dollar question is, does it actually work? What did the experimental results show about the impact of proto-reasoning?
Well, the results were genuinely compelling. Incorporating this synthetic Prolog and PDDL data led to really substantial gains across a variety of reasoning benchmarks.
Okay, like what?
So, on logical reasoning, they used the Enigmata Evil benchmark. Performance increased overall by 4.7%. And notably, within that, for the crypto tasks, which involve things like deciphering codes, There was an impressive 11.0% improvement.
Wow, 11%. That's a significant jump.
It really is. And for planning tasks, they saw a solid 6.3% improvement, plus a 6.4% improvement on function calling using the Nexus Hard benchmark, which often requires a similar kind of sequential action formulation like planning.
So consistent gains across related tasks.
Exactly. These improvements weren't just marginal, they were robust and significant pretty much across the board for these targeted areas.
But here's where it gets really interesting, right? The part that truly tests their core hypothesis, the cross-domain generalization. Did proto-reasoning just improve the specific logic and planning tasks they trained for, or did it generalize?
This is the crucial validation of their concept. And yes, it did generalize. Proto-reasoning showed strong generalization to entirely unrelated domains.
Like what?
Performance on the General Reasoning Benchmark, MMLU, that's a broad measure of multitask understanding, jumped by 4.0%.
Okay, that's impressive.
And even on mathematical reasoning, specifically the AINARY 2024 benchmark, they observed a 1.0% improvement. Now, 1% might sound small, but improving high-level math reasoning is notoriously difficult.
Absolutely.
So this strongly confirms that training with these abstract reasoning prototypes enhances overall general knowledge reasoning and even mathematical skills. It validates the idea that learning these fundamental patterns pays off broadly, even in areas the model wasn't explicitly trained on using these prototypes.
So to really nail down why these prototypes are so effective, the researchers did what's called an ablation study. Can you explain that? What was the core question they were trying to isolate here?
Sure. The core question in the ablation study was to isolate the impact of the prototype representation itself. They wanted to know, is the benefit coming from the logical content of the problems, or is it something specific about presenting them in that abstract, formal prologue structure?
Content versus format based.
Exactly. Is it the what or the how it's presented that really matters for generalization? So they meticulously set this up. They took a subset of a benchmark, Enigmata Evil, I believe, and created two versions for training.
Okay.
One version presented the problems formally in prologue. The other presented the exact same problems, but written out in natural language. So the underlying logic, the content, was identical, only the format differed.
Clever comparison.
Yeah.
And the results, what did they find?
The results were quite clear. Training with the formal prologue representations led to significant performance gains on downstream tasks, and these gains were comparable to the gains achieved by training directly on the natural language versions of those same problems.
Comparable. So the format mattered as much as the content.
It strongly suggests that.
Yeah.
It implies that the abstract structure captured by the prototypes is a key driver of the generalization benefit, even when that learned knowledge is later applied to problems the model sees in natural language.
Fascinating.
It also confirms something else important, that explicit reasoning processes, like using chain of thought during training, are pretty essential for this effective generalization through prototypes. You need both the abstract structure and the explicit reasoning steps.
This work really seems to introduce reasoning prototypes as maybe a fundamental concept for understanding how LLMs generalize. It gives us a more foundational framework for enabling this cross-domain reasoning transfer, building on important previous work like long Cody and symbolic reasoning in LLMs, but maybe giving it a more concrete mechanism.
I think that's a fair assessment. And what's fascinating is that the researchers believe this framework could potentially be generalized to other LLM capabilities too, beyond just logic and planning.
But they also acknowledge limitations.
Oh, definitely. They're clear that the precise definition of what constitutes a reasoning prototype needs more formal mathematical rigor. And the underlying mechanisms, exactly how the model internalizes and transfers these patterns, still requires deeper investigation.
So what's next then? Where does this research go from here?
Well, the paper outlines a few key directions. Future work includes developing more rigorous mathematical frameworks to really pin down and characterize these prototypes.
Okay.
They also plan to open source the curated data sets they created, which is great for the broader research community to build upon and verify.
That's always good to see.
Absolutely. And reproducing the results on other open source LLMs is also key to ensure the findings are broadly applicable and not just specific to the models they used. It's definitely a field that seems ripe for further exploration.
So let's try to wrap this up. What does this all mean for our understanding of AI? We've seen how this proto-reasoning approach uses abstract reasoning prototypes represented by these powerful, verifiable languages like Prolog for logic, PDDL for planning, to give LLMs what seems like a deeper, more generalizable understanding of how to solve problems. It feels like by distilling problems down to their core structural essence, These models are moving beyond just memorizing answers. They're learning the fundamental blueprints of thought, maybe.
That's a good way to put it. It certainly feels like an exciting leap towards more robust and, dare I say, genuinely intelligent AI systems,
Uh-huh.
systems that can adapt and apply knowledge across diverse challenges much more effectively.
Right. And it really makes you wonder, doesn't it? If abstract reasoning prototypes are indeed a foundation for generalizable intelligence in LLMs, well, what does that imply about us, about human learning?
Hmm.
Are we too constantly abstracting and applying these fundamental patterns of thought across all the new and diverse challenges we face in our own lives, maybe often without even consciously realizing it?
It's a fascinating parallel to consider.
What new problem could you tackle, perhaps, by stepping back and trying to identify its underlying reasoning prototype?